Hello everyone. In this video, we're covering topics from the course of Chemistry 1412, also known as General Chemistry 2. So in this video, let me go ahead and expand this for you. We're going to be covering equilibrium state, equilibrium constant, which is going to be shown with the Kc, reaction quotient, which is Qc, and direction of reaction, and Kp. Kp is also going to be an equilibrium constant, but dealing with partial pressure. The first topic is equilibrium state. A forward reaction is going to be when you're moving from your reactants to a product. This is what we normally seen or have seen so far in our course. But there is also a reverse reaction. So, as you can tell, it's going to be from products to reactants, so the exact opposite of our forward. Reactions are capable of having both a forward reaction and a reverse reaction. When a reaction's forward process and reverse process are perfectly balanced, the reaction is in equilibrium. At equilibrium, the concentrations of the product and reactants no longer change because the rates of the forward and reverse reaction are going to be equal. So as you can see at the bottom, at equilibrium, we're moving at a rate forward and reverse at equal rates. The equilibrium constant. The equilibrium constant, which can be seen as K, Kc, or Keq, is used to determine the ratio of product concentrations or reactant concentrations for a given reaction. Given the reaction, A plus B yields C plus D, the equilibrium constant is as defined. So, our uppercase letters are going to be our compounds or our molecules that we have in our reaction, while the lowercase is going to represent our coefficients for those compounds or molecules. For the equation of our equilibrium constant, we have K equals the concentration of our products, so C and D, over the concentration of our reactants, A and B. You should also notice that the lowercase letters, which was our coefficients in our reaction, as you see the little a, b, c, and d, are now the exponents in our equation. So make sure you pay attention and put those into your actual equation, otherwise it'll throw all your numbers off. Reaction quotient. For reactions that are not at equilibrium, we can write a similar expression to the equilibrium constant called the reaction quotient, which we can see as a Q or QC. Sometimes you'll see it as the same thing as KEQ, you'll see it as QEQ. The reaction quotient Kc is equal to the equilibrium constant when at equilibrium. So what you'll notice is that our QC equation is the exact same equation we saw for Kc, or the equilibrium constant. So you're still going to have the concentration of your products over the concentration of your reactants, where your coefficients are now your exponents. Kc and QC can be used to determine if a reaction is at equilibrium, to calculate concentrations while at equilibrium, or to estimate whether a reaction favors the products or if it favors the reactants when the reaction is at equilibrium. So let's practice writing the reaction quotients. So this problem says, write the reaction quotients for the following reactions. Part A is the decomposition of dinitrogen pentoxide, which is N2O5 yields NO2 plus O2. And then part B is going to be the combustion of propane. So we have C3H8 plus O2 yields CO2 plus H2O. So the solutions. So for part A, we have to put our products first. So we have our NO2 and our O2, while remembering our coefficient for the NO2 is now the exponent. And then at the bottom, we put N2O5, where the coefficient of 2 now becomes an exponent of 2. For part B, same thing, we'll do our products over our reactants. So we have CO2 times H2O, where the coefficient of 3 on the CO2 becomes an exponent, and the coefficient of 4 on the water becomes its exponent. Then we move to our reactant side, so the bottom or denominator of our equation, and we say C3H8 times O2, where our coefficient becomes an exponent of 5 on that O2. Continue. If Kc is small, so if our equilibrium constant is small, which is around 0.001, it indicates that the reaction yields little product before reaching equilibrium, which means that our reaction is going to favor our reactants. If our Kc is large, so estimated around 1,000, it indicates that the reaction has little reactants remaining at equilibrium, and our reaction will favor our products. If the Kc falls before the previous two or in between the previous two, neither of the products or reactants are favored. So if it's anywhere in between our 0.001 or our 1,000, it's going to favor neither side. Practicing the concept. Which of the following reaction is the equilibrium at temperature T, with the given equilibrium concentrations of SO2 equals 0.90 molar, O2 equals 0.35 molar, and SO3 equals 1.1 molar. Calculate the equilibrium constant K and determine which side of the reaction is favored. So they provide us with an already balanced equation, so we have to figure out what we know to be able to solve this. We know that the format of our equilibrium constant K is going to be the concentration of our products divided by the concentration of our reactants. We also know the concentrations for each of our products and reactants. So we can begin to plug it in. So we plug it in with just our compounds first. So our products of SO3 to the second power divided by SO2 to the second power times O2. So we can plug those concentrations in and solve for K. So 1.1 to the second power divided by 0.9 to the second power times 0.35. And when we plug that in, we should get a K of 4.30. Because 4.30 falls in between 0.001 and 1,000, our reaction is going to favor neither side. Continue. Using the equilibrium constant from the previous example, imagine we have the same reaction at the same temperature, but the concentrations change to SO2 equals 3.600 molar, O2 equals 0.087 molar, and SO3 equals 2.200 molar. Determine if this reaction is at equilibrium. And then they provide us with the balanced equation already. So what do we know? We know that when our reaction quotient, Q, equals our K, then our reaction is at equilibrium. And we know that they want us to use the K from our previous example, which was 4.3, so we can solve for Q. So the equation is our products divided by our reactants. So the same exact way for solving for K. So we have SO3 to the second power divided by SO2 to the second power times O2. We plug that in, and we'll end up with a Q of 4.3. And because our Q equals the K that we previously calculated, we know that this reaction is also at equilibrium. So let's work another example. Given our K equals 3.5 times 10 to the negative 21, and the equilibrium composition is N2 equals O2, which is going to be equal to 0.1 molar, determine the concentration of NO in grams at equilibrium. And then they provide us with the balanced equation below. So now, we're not solving for our K, we're actually given it. We're trying to find one of our concentrations. So what do we know? We know that K equals the concentration of our products divided by reactants. So NO to the second power divided by N2 times O2. We were also given our K, so we know we can plug that into our equation, which was 3.5 times 10 to the negative 21. And we were given two of our concentrations, which is N2 and O2, both of which are 0.1 molar. So let's plug in the information we have. Well, we know that the basic K equation will be a little bit difficult to try to solve for what we need, so we can manipulate the equation to get NO by itself. So what we do is use basic algebra. We know that because it's dividing on the right side, we can multiply into O2 on both sides to get rid of it on the right side. So we'll end up with K times N2 times O2 equals NO2, or sorry, NO to the second power. And because it's squared and we want to get it by itself, we square root both sides. And we know that to find the concentration of NO, we have to take the square root of K times N2 times O2. So we can plug in our values. We plug in the square root of 3.5 times 10 to the negative 21 times 0.1 times 0.1 equals NO. So the concentration of our NO is going to be 5.8 times 10 to the negative 12 molar. Forms of K and Q. An overall reaction is the sum of two or more individual reactions. So our K overall is going to be K1 times K2 times K3, and however many reactions you actually have occurring. This is going to be the exact same for our QC or our Q. So the Q overall will be Q1 times Q2 times however many you have. The form of Q and K depend on the direction in which the balanced equation is written. So for instance, if we have a forward reaction, we simply do 1 divided by either our K or our Q forward, and that will give us our QC or KC reverse. You can also do this the exact opposite way. So if you have your reverse and you're trying to find your forward value, you simply manipulate the equation to be able to get what you're looking for. So let's do a practice question. Nitrogen dioxide is a toxic pollutant that contributes to photochemical smog. One way it forms is through the following sequence. So we have two different reactions occurring. So N2 plus O2 yields 2NO, which has a Kc of 4.3 times 10 to the negative 25. And the second reaction being 2NO plus O2 yields 2NO with the Kc of 6.4 times 10 to the 9. For part A, show all of the overall QC for this reaction sequence as the same as the product of QCs for the individual reactions. In part B, given that both reactions occur at the same temperature, find the Kc for the overall reaction. So take note that it said the Kc for the overall reaction. So for part A, before we get started, we have to cancel out the items that are identical on the left side of one and the right side of the other equation. So for instance, we have 2NO on the left side of reaction 2 and 2NO on the product of reaction 1. So those two will cancel out and everything will come down. So our overall reaction is going to be N2 plus 2O2 yields 2NO2. And our QC will kind of mirror that. So this is our QC for reaction 1, our QC for reaction 2. We notice that we have to cancel out just like we did up here. And when we cancel out, we'll end up with the exact same overall. So our product of NO2 to the second power divided by our reactants, which is N2 and O2 to the second power, and that would be our overall QC. And now for part B. So remember, to find the overall reaction, we have to multiply all of our K's. So for our overall KC, so for the KC for this overall reaction right here, we have to multiply these other two KC's. So we multiply 4.3 times 10 to the negative 5 times 6.4 times 10 to the 9, and we'll get our overall QC. Practice the concept. Consider the reaction of cadmium with thiosulfate anion. So we have our two different reactions, just like we did in our previous example. They want to know, what is the equilibrium constant for the following reaction? So, just like before, we're trying to find our overall K, because the equilibrium constant is our K value. And what we'll notice is that the following reaction is an overall reaction for the previous two. So the CD-S2O3 is on both sides of the reaction, or on, the left side of our second reaction and the right side of our first reaction, so they can cancel out. Nothing else can cancel out, so it will come down, and we end up seeing this third reaction right here. So after it all cancels out, we simply do our overall reaction equation, which is multiplying our K values. So we do 8.3 times 10 to the third times 2.5 times 10 to the 2, and we'll end up with an overall equilibrium constant of 2.1 times 10 to the 6. K and Q for the heterogeneous equilibrium. A heterogeneous equilibrium involves reactants and or products in different phases. So as you can see below, we have two solids and we have a gas. A pure solid or liquid always has the same concentration, i.e. the same number of moles per liter of solid or liquid. The expressions for Q and K include only species whose concentrations change as the reaction approaches equilibrium. Pure solids and liquids are omitted from the expression of Q or K. For the above reaction, our Q would be equal to the concentration of CO2. That is because these solids will not get taken into account. Determining the direction of a reaction. The value of the reaction quotient in comparison to the equilibrium constant indicates the direction of a reaction. So if our Q is less than our K, the reactants decrease and the products will increase, which means that we will be moving from reactants to products. If our Q is greater than our K, the reactants will increase and the products will decrease, which means that we're moving from products to reactants. And if our Q is equal to our K, the system is at equilibrium and no net change will occur. So let's work an example. 0.5 moles of SO2Cl2, 0.035 moles of SO2, and 0.080 moles of CO2 are combined in an evacuated 5-liter flask and heated to 100 degrees Celsius. What is the direction the reaction is moving given the following? And so we're given our reaction and we're given our K value at 100 degrees Celsius. So what do we know? We know that our K is equal to 0.078. We also know that our QC is going to be our concentration of our products divided by our reactants. So SO2 times Cl2 divided by SO2Cl2. And we can try to plug in, but you have to take into account that we're given our values in moles. And to plug it in, we have to have concentration, which is going to be in molarity. Molarity is going to be moles per liter. So that's where that 5-liter flask comes in handy. So we'll take the moles and we're going to divide it by the 5 liters because of that 5-liter flask. And we'll be able to get the molarity for each of our values. So 0.50 moles divided by 5, we'll end up getting 0.1 molar of SO2Cl2. 0.035 moles divided by 5 will give us 0.007 molar of SO2. And 0.080 moles divided by 5 will give us 0.016 molar of Cl2. So we can plug in our concentrations now. When we plug in 0.007 times 0.016 divided by 0.1, we'll get a QC of 0.001. What we notice is that our Q is smaller or less than our K. So the reaction is going to move from reactants to products in a forward reaction. Calculating equilibrium constant Kp using partial pressure. The equilibrium constant Kp describes the ratio of product and reactant concentrations at equilibrium in terms of partial pressure. For the gas phase reaction A plus B yields C plus D, our Kp is going to be the pressure of C to the C power, so our coefficients are still our exponents, times the pressure of D, so this is going to be the partial pressure or the pressure of our products divided by the pressure of our reactants, where our coefficients are still our exponents. So let's practice. At temperature T, given the pressure of N2O5 equals 2 atm, O2 equals 0.296 atm, and NO2 equals 1.5 atm, what is the equilibrium constant Kp? And they also gave us a balanced reaction below. So what do we know? We know that Kp is going to be the pressure of our products divided by the pressures of our reactants. So that'll be the pressure of O2 times the pressure of NO2 to the 4th power divided by the pressure of N2O5 to the 2nd power. So we can plug in the pressures they provided. So we'll do 0.296 times 1.7 to the 4th power divided by 2 to the 2nd power. And that's going to give us a Kp of 0.618. And now we're going to talk about how to find our Kp from our Kc. So Kp is related to Kc in terms of molar concentration using the following equation. So Kp equals our Kc times RT delta N. So what you notice is they're both equilibrium constants. However, Kp deals with pressure while Kc deals with concentration. That's what that subscript letter is. And then the delta N is going to be moles of gas product minus moles of gas reactant. And this will make a little bit more sense when we work some examples. So let's practice. If Kc for this reaction is 4.5 times 10 to the fourth at 400 degrees Kelvin, what is the equilibrium constant Kp at the same temperature? And they provided us with the balanced reaction below. So we know that Kp equals Kc times RT delta N. Kc is 4.5 times 10 to the fourth. Our R is just our constant, so 0.08314, times our temperature of 400 Kelvin, and then we have to determine what our delta N is. So it's going to be our moles of gas product, which would be moles of NH3 minus our moles of gas reactant, which is the moles of N2 plus the moles of H2. So we have 2 moles of product minus we have 1 mole of N2 while we have 3 moles of H2, so we add those together. So we'll end up doing 2 minus 4, which would give us a delta N of -2. So we can plug it all in. Kp equals 4.5 times 10 to the 4 times 0.08314 times 400 to the -2 power, which will give us a Kp of 41. And that is all we pretty much have for today. So let's do a brief overview of everything we covered. We covered the equilibrium state, which states that the forward and reverse reactions are equal when at equilibrium. We also covered the equilibrium constant Kc, but we can also see it as K and Keq. And to find K, it's going to be the concentration of your products divided by the concentration of your reactants. We also covered the reaction quotient, which is very similar to our equilibrium constant in the way that it's going to have the exact same equation. So the concentration of our products divided by the concentration of our reactants. The fourth thing we covered is the direction of a reaction. So when our K value, or our reaction quotient, is less than our equilibrium constant, we're going to be moving from reactants to products, which means that we have a forward reaction. We also know that if our Q is greater than our K, we're going to be moving from products to reactants, so we'll have a reverse reaction. And then the final concept that we covered is Kp, which is the equilibrium constant when dealing with partial pressure. So there's 2 different equations that we can use to find Kp. The first is pretty much similar to our equilibrium constant and reaction quotient, where we're going to do our products over reactants, but instead of concentration, we're now doing pressure. So it's going to be the pressure of your products divided by the pressure of your reactants. And then the second equation is Kp using, or finding Kp using our Kc. So if our Kc times our R, which is our gas constant, times T, our temperature, raised to the delta N. And that'll be another way that we can find Kp. It's really just based off of the type of question and information that is provided. So that is all that we have today. I wish you best of luck on these topics and hope you enjoyed this video.